Okay, for the final speaker of the final moments here, yes, you get to cap off today and this session. So it's going to be TJ Wignall. He's a aerospace engineer with NASA Langley, and the talk C is a calculation of continuous surrogate load distributions from discrete resample data. Take it away, TJ.
All right, thank you very much. Did I mess this up? No.
There
All
we
right.
go. Yep.
Now that I broke it, I fixed it again. Okay, so this talk is about using resampling to better improve surrogate modeling. So a lot of these talks this week have been using uncertainty via surrogate models. It's very common, still more state of the art than state of the practice. This is especially common when we have very expensive high fidelity data. Um, the work kind of focus here focuses more of the how good is our circuit model itself? What is the uncertainty of the circuit model itself? There is stuff out there in the literature. The focus we have been working on is distributed spatial predictions. I'll show an example later, but we are interested in the kind of the sectional loads, the loading over an area, and so want to kind of keep as much of this spatial correlation data as possible. So I haven't found much on this sort of stuff using that focuses on dispersed spatial predictions. For this work, we're going to be using a modal decomposition type surrogate model. In this case, principal component analysis with interpolation. Same general uh, as proper orthogonal decomposition and empirical orthogonal functions. I gave some initial work I showed at AAA SciTech in January, and that showed that these resampling methods do give us an insight to the underlying distributions of what's going on, and then we can then use those distributions, we can fit a model to it, and then we can disperse predicted forces and moments. One thing that I'll show briefly is we get these two clusters in our data, and we hypothesize that one is an artifact of the discrete nature of the resampling, which is what we're trying to address here today. So we're going to be looking at that secondary cluster, and we're going to show off that we can use these methodologies to get spatial predictions, not just integrated forces. So just quick overview, so we all know are on the same page when I say PCA plus interpolation. We get a matrix of solution snapshots X. We do a modal decomposition, so we get our principal component psi times a coefficient matrix. We're making our coefficient matrix normalized, so all the values are between -1 and 1. And then the principal components are going to characterize the spatial information, and they're going to be scaled by singular values or eigenvalues, whatever you want to say, but they incorporate the variance, so they're not normalized. We know these values of a transposed where we have snapshots where we've gathered data. And so we can take that and we can interpolate across the domain of interest. We're going to call this B. You can slightly do different forms of the model by doing some sort of regression analysis instead of interpolation. And it kind of carries through. So we get this B. And then what we can then do is then we can recombine our principal components with these interpolated coefficients. And if we're only interested in one point in one parameter space, we can just kind of do a summation. So we get predicted value of y at surface of interest S at parameter point P. Or we can just do the whole matrix multiplication, get all of our surfaces or flow fields of interest at all of our parameter points at once. So the problem is it's very difficult to compute the statistics on the interpolated coefficients of B. So we've looked at bootstrapping to approximate those underlying statistics. So we're going to be using resampling. In this application, what we do is we take our snapshot matrix X and we just drop different columns. We get X prime, and we go through the process again, and we get our subscript versions of psi sub B and B sub B. And then we get our bootstrap prediction, Y sub B. And we want to quantify the accuracy of the surrogate model by analyzing these bootstrap predictions. However, it is difficult to do this because our dimensions between B sub B and B are different because as we change the number of snapshots, we're changing the dimension. So we can't do a direct mapping between one to the other. So what we're going to do is we trust the baseline principal component psi, and we say, what do we have to multiply to get the equivalent of our bootstrap prediction? And so we introduce this B star. So we can solve for B star here. But we kind of want to end up with a distribution around 0. So we actually solve for the residual instead. So we take the difference between our baseline prediction y and our bootstrap prediction, and we actually set it up so we solve for this little b, which is the coefficient residual matrix. So solving for b, we get variations of the original coefficient matrix that account for the drop data. Um, as a representation of the modal basis sensitivity, and as I'll show, the interpolation scheme as well. And it's extends to interpreting the unknown values in our predictions. So at SciTech, I showed some results using this simplified tactical fighter. We're using CFD data from the USM3D mixed element flow solver. These are RAND solutions with an SA turbulence model. This work, we're only focusing on the surface pressure of the vehicle, although it's pretty easy to extend to other quantities of interest or the whole flow field, but it does make the problem bigger. We do a simple 2-parameter study of Mach and angle of attack. And what we do is we showed the ability to resample to get the distributions on integrated coefficients and then apply those distributions to a force and moment. So we got a bunch of plots that look like this histogram of little b1. On the left, we have the absolute value, and on the right, we have the natural log of the absolute value. So this is a coefficient associated with the first principal component. And our work at SciTech showed we do get this kind of dual cluster result when we look at the log transform. And as the mode number increases, just for a note on nomenclature, I call the rightmost cluster the primary cluster, and the left one the secondary cluster. Because as mode number increases, what we see is that secondary cluster move closer and closer and eventually moves to the primary cluster. And so we have one of these plots for each of our retained modes. And it's unclear of the cause of the secondary cluster, but we did find it was pretty common no matter what knobs and settings we changed. So that'll be the focus of the work here, which I'll talk about after this slide, which is just showing that we can take that exponential fit that was on the plot on the last slide, and we can use it to get force and moment predictions. So this is lift, drag, and pitching moment, left to right. At the top, we have a constant Mach number with an alpha sweep, and on the bottom, we have a constant alpha with a Mach sweep. Our gray box is a 90% interval with the black line being a nominal prediction. And then we have test data in orange circles and training data in blue squares. The red dots are the different resample predictions. As we went through the resampling process, we can get predicted forces and moments. And so you can see pretty good agreement between the red dots and the gray interval, kind of except drag, where we see the gray interval being significantly larger. And then pitching moment, we do see the limitations. We're using a linear interpolation we did use a linear interpolation for that work. So if we miss kind of a corner point, we can see a drop off as it matches to a different point. Here you can see that, and then also in the bottom right with Mach equals 0.9. So we were pretty happy with that, but we kept going back to that secondary cluster, like what is causing it? And so what we theorized is that the secondary cluster is from how we remove snapshots. These snapshots are a big part of this information system, and every time we remove a snapshot, it's removing a lot of information. And typically when you do sensitivity analysis, we want to be able to control the severity of perturbation. So we thought, okay, so if there's some way we can change the influence of individual snapshots, we can then control the severity of the data removal. So what we decided to look at is kind of changing our model. We're using now a weighted singular value decomposition. So for our first model, we had just kind of the covariance eigendecomposition to get our principal components in A. We then kind of do a mean centering on our snapshot matrix X, introduce this W term here, and then do a SVD, so kind of just a weighted singular value decomposition, and rebuild our model. And then we kind of do the same thing. We get B from the interpolating A across the region. And we can change the very influence of each individual snapshot if we want, although we kind of just group them as I talk about here. So if weight of 0, if we weight a snapshot 0, that is equivalent to full removal. When we do that, we see that we're getting our original results of the full removal. And what we do is we're varying the weights from 0 to 1. They're either a value of 1 or a new non-identity weight, which gets you at the bottom. but 1/3 of the snapshots have varied weights, 2/3 of snapshots have the identity weight. Any snapshot with a non-identity weight, we actually don't use interpolation because that would recreate the weighted snapshot instead of the original snapshot. We have some ideas of how to work around that, but we haven't gotten to it yet. And we look at 4 different weights, a value of 0, which as I mentioned is equivalent to full removal, 0.5, 0.9, and 0.999. As we get closer to 1, we actually get closer to just accounting for the interpolation scheme, which we'll see in a few slides. To switch it up, we did a more complicated problem. This is a 3-body launch vehicle, simplified a rocket that looks a lot like SLS. But without any of the cool perturbations and a lot nicer round values for the vehicle. Here we're using 60 CFD solutions using Kestrel Flow Solver. This kind of was our entire computational budget of the case of the campaign, and so we don't really have a lot of evaluation points that we held out, and that's kind of why we've been looking at resampling methods, is because these cases are relatively expensive. And so we want to use every single data point we have. Here we're using hybrid RANS LES, time average surface pressures. You can see that it's a large wake dominated flow at these conditions. So we definitely need the time averaging to smooth things out. Here we're doing a 3-parameter study. We have angle of attack, roll angle, and Reynolds number. This is a low speed flight regime. The Mach number is about Mach 0.2. So it's low speed and more or less incompressible. This Reynolds number variation is kind of the span from a testing Reynolds number to a flight Reynolds number to kind of measure if the Reynolds number has a effect on, final values. But as we apply this process to this new problem, we get similar results. We do see the effect of weighting here. This is, again, histograms of little b1. Here in blue, we have weights of 0. In orange, we have 0.5, green 0.9, and then red is the 4 nines. And so what we see is as the weight increases, we actually see that secondary cluster move left as we hope. The amplitude doesn't change significantly. It gets a little bit wider, so maybe the same number of points are in the secondary cluster regardless of weight, but we didn't do that analysis. One thing we see with this problem is, unlike the previous simple fighter, is we're actually seeing more points in the secondary cluster than the primary cluster, and that primary cluster is incoherent. It's way less coherent than the original. So that made us sit down and it's like, well, is something wrong with our surrogate model? Can we improve it somehow? This process, we focused on, can we quantify the effect of the modal decomposition? But what we realized is we're actually quantifying the fidelity of the entire surrogate model and not just the modal decomposition. This is a complex flow regime, as this picture shows. This is vorticity as we simulate through time, coming off of the wake. It's a relatively sparse data space in a very complex flow regime, so that interpolation is actually really important. So we're like, well, can we use this methodology to evaluate and decide which interpolation scheme we should be using? So we implemented and used a inverse distance interpolation as opposed to just a linear interpolation, since it scales well to higher dimensions. And we can get similar plots as before with the forces and moments. At the top, we have linear interpolation. On the bottom, we have inverse distance interpolation. These are alpha sweeps at a roll of 0 and a 10 million Reynolds number. And again, we don't have any test data here because it was so expensive to generate in the first place. Here we can see definitely the failure of the linear interpolation where we're cutting these corners as we go up an angle of attack. That's not being captured very well. With the inverse distance interpolation capturing that much better even as it goes through. We don't see a huge difference in the gray region, although the gray region with the inverse distance is a little bit tighter. But overall, the nominal prediction is where we expect it to be, so that's good to see as well. But when we look at the histograms of little b1, we still have that secondary cluster. but it's much lower magnitude, and that primary cluster is much more coherent. And we do see that the weights are still controlling the secondary cluster. So this is the same data, same sort of data plot as before, where we have a weight varying as we change colors. One thing that was interesting was that secondary peak location and movement appears independent of interpolation scheme. Here we have the blue, orange, and green. We have the linear interpolation, while in the red, purple, and brown, we have the inverse distance interpolation. What you see is that secondary peak location seems to line up between the weighting pretty consistently. But we do see that inverse distance being much better behaved, so we see and have judged that the inverse distance is much better for this application here. And as we go up in mode number, this is mode number 19 on the left and 49 on the right. We can see that this is how the secondary cluster merges with the primary. You can see that in these plots. But we do see that definitely the 0.999 weight of secondary cluster stays lined up at 19 and 49. A little bit harder to tell, but the 0.5 and the 0 have some lining up as well. So we do think this might be a more universal thing that we still want to explore. But as I mentioned, we are really concerned about the spatial characteristics underlying spatial coherence. And so these are the line loads. For those who aren't familiar, line loads are pretty much you take the forces on different slices of the vehicle and you add them all up and you can plot them as a function of x. So we have the normal force on the top and then side force on the bottom. So the solid black line is our nominal prediction from this model. The gray box is a 90% interval still. And then the green lines are random individual predictions. One thing that we really like about this method versus kind of our naive increment-based approaches we've been using previously is that we are kind of crossing the nominal here as we go through. Because one of the concerns is when you're doing this sort of the loading analysis being used with these line loads, you're not just necessarily worried about the integrated forces, but also kind of the shear stresses. So being able to change the slope implicitly, changes the shear stresses that will be captured in any downstream analysis. So really happy with that. So just some quick conclusions. Resampling the snapshot matrix for modal decomposition type surrogate models. It's a way that we can develop a new model with some sort of noise. We do retain that coherent spatial characteristics, allowing for predictions of surfaces and line loads. So you saw the line loads. Surfaces are a little harder to plot, but it is there in the background. We can use it to evaluate and compare different models. So we can do it as a kind of a model shopping sort of way. But the overall shape of those resampled coefficients is very dependent on the interpolation portion of the surrogate model. And we saw that weighted SVD does allow us to control the secondary cluster, but that primary cluster is pretty much driven by interpolation scheme. So the current method we have kind of combines the effect of both of those, both the interpolation and the modal decomposition. But I think there's definitely a path forward to kind of split those in the future. That remains future work. Thank you.